Parallel combination of bulb. Okay. Now if I connect the bulbs in parallel, so what is parallel? Actually here voltage same but current divides, right? So here it has got some power rating PR2, and of course the voltage rating is same. Here PR1 but voltage rating is same. Okay, some voltage we applied, let us say some voltage, and delivered some current. This is I1, this is I2. Okay, we know that R1 is equal to VR square by PR1, R2 is equal to VR square by PR2. Yes or no? We already know that R is inversely proportional to PR all the time. Okay, and we would like to compare even the powers. Power consumed by the bulbs we would like to compare, and we will see how actually they are glowing. Which one is glowing brighter than the other, we would like to compare. Okay, but what are the formulas that we have? P is equal to I square R. P is equal to V square by R. Okay, this I is an operating current, operating voltage. Yes or no? Operating voltage is same here, right? For both these elements. So better we choose this formula to compare, because current is getting divided. To compare, I think it is better to use P is equal to V square by R formula. So power consumption, okay, power consumption of the first bulb, okay, power consumption of the first bulb is V square by R1. Power consumption of the second bulb is V square by R2. Now from this, we can say power consumption is inversely proportional to R. Yes or no? Now from these two formulas, we can understand that power consumption, look at this, R is inversely proportional to PR, but already R is inversely proportional to P consumption. Finally, power consumption is directly proportional to what? Power rating. Now from this, we understand that, okay, the bulb with a higher rating will consume higher amount of power. So power consumption of the bulb 40 watt will be less than power consumption of the 60 watt. Okay, so which one glows brighter? Now 60 watt bulb glows brighter than 40 watt. Yes or no? Okay, so this is very, very important. That is why whenever we want in our domestic applications, we want more brightness, then we go for higher rating bulb, because all bulbs are connected in parallel. Yes or no? Okay, but in case if you connect them in series for any reason, then which one glows brighter? 40 watt bulb glows brighter than what? 60 watt bulb, that we have already seen in the last session. Okay, you can please note down all these things. Quickly note down this very, very important part. Okay, I think all of you are noting down that. Okay, quickly please move that. Okay, now let us look at some problems on this classroom workbook. What is the question number? You can see 41. Okay. This was asked in GATE. Okay. Now, read the question. All of you, please. Two incandescent light bulbs of 40 watt and 60 watt rating are connected in series across the mains. Then, look at the four options given actually here. I repeat once again. Two incandescent light bulbs of 40 watt and 60 watt rating are connected in series across the mains. Then, A. The bulbs together consume 100 watt. Is it correct? I don't think so. Okay, because the elements are connected in series. When elements are connected in series, the voltage gets divided. When voltage gets divided, its operating voltage, okay, operating voltage and rated voltage both are different. Yes or no? If you apply 230 volts, the 230 volts is getting divided for the two bulbs. So we do not know how much voltage is appearing across each bulb. Okay. And finally, the power consumption of the 40 watt bulb is not going to consume 40 watt. 60 watt bulb is not going to consume 60 watt. Yes or no? So you cannot say 60 plus 40 is 100. Most of the times people may do mistake when first case is very tempting option, first option. Okay. So be careful. That's not the correct option. The bulbs together consume 50 watt. When I'm not sure about 100 watt and I'm not also sure about 50 watt because I do not know how much voltage is appearing across each and every bulb and what is the voltage rating and all these things. It's not possible. You cannot say. Option C. 60 watt bulb glows brighter. Obviously not. A bulb with a lower power rating will consume higher amount of power and that glows brighter than the other, right? We have seen already in the series combination. Then obviously the last option is left over. 40 watt bulb glows brighter. So please choose the option. What is that? Option D is the correct option. Next we move on to classroom workbook. Question number 42. Question number 42. Okay. Look at this. All resistances in the figure are of R ohm each. Okay. The switch is initially open. What happens to the lamp's intensity? What happens to the lamp's intensity when the switch is closed? What happens to the lamp's intensity when the switch is closed? Okay, I think all of you understand that question. First, initially, the switch was open. When the switch is closed, what happens to the lamp's intensity as compared to when the switch is open? Okay, so let us look at that. This is what the switch. 220 volts is the mains. This is the lamp. Okay. Now, look at this. Initially, the switch is open. Yes or no? Initially, the switch is open. Now, what happens to the lamp's intensity when the switch is closed? Okay, what will happen? In the first case, when the switch is open, you can find what is the current flowing through the lamp. In the second case, you find what is the current flowing through the lamp. Okay? In whichever the case, the current flowing through the lamp is higher, so that I square R dissipation is higher. Okay? In that case, definitely the power and the intensity will be higher as compared to the other. Is it clear? Now, look at this. Each resistor value is R. That means all are having same value. When all are having same value, it is a bridge Wheatstone bridge, and that too balanced bridge because of all elements are having the same values. Particularly these values. I'm not worrying about this, but I'm worrying about these values here. R balanced. Irrespective of this value, R is balanced. If it is balanced, what will happen? Under balanced condition, whether switch is open or switch is closed, equivalent resistance, does it change? No. Then current delivered by the source, does it change? No. Then the intensity of the lamp, power consumed by the lamp, does it change? No. So what are the four options given? Option A increases, option B decreases, option C remains the same, option D depends on R value. What is the option here? Remains same. What is the reason? What is the reason for the option C that we are choosing here? Because the given one is a balanced Wheatstone bridge. Okay, so please write down here. Since it is a balanced Wheatstone bridge, all of you write down. Since it is a balanced Wheatstone bridge, since it is a balanced Wheatstone bridge, okay, the current through the lamp, comma, the power consumed by the lamp, the current through the lamp, comma, the power consumed by the lamp, and hence the intensity of the lamp will remain same, for both switch open and closed conditions. For both switch open and closed conditions. Okay, therefore, what is the option? Option C is correct. Okay, so these are the variety of problems that we can see. Totally 42 problems we covered in this topic. Okay. Now, the topic that is fundamentals of DC circuits. Okay, is covered. In the next topic, we move on to now methods of analysis. Okay, methods of analysis. We'll move on to next topic, that is methods of analysis. Note down methods of analysis. Okay, particularly I start with mesh and node analysis, and after that I'll go for DC theorems. Okay, methods of analysis. Okay, and in this I'm going to discuss what? Mesh and node analysis. So DC circuits was divided into fundamentals of DC circuits, okay, and DC steady state analysis. In the DC steady state analysis, we have taken methods of analysis and DC theorems. Okay, so we deal with the next topic, that is methods of analysis, that is mesh analysis, node analysis with you. Okay, so before that I would like to generalize, because in engineering, okay, in engineering, especially when you deal with the problem, particularly electrical or electronic students or instrumentation students, particularly all these three branch students, when you come across any problem, any situation, okay, to analyze a particular system, okay, the analysis can be of two types. Yes or no? Okay, what is that analysis? Analysis can be done in two different ways. What is that analysis? Network analysis. Okay, network analysis can be done like this. Just for knowledge sake, I'm telling you this, and we'll straight away go to the node mesh analysis, because one must be really aware of this completely here. Okay, so network analysis is of two types. One is steady state analysis. One is steady state analysis. The other is transient analysis. Okay, if somebody is giving any system or any network and ask you to analyze it, immediately you are supposed to question that which type of analysis you want. You want me to go with steady state analysis or transient analysis? It must be very clear. Okay. Now that is why there are two types of analysis you can do on a particular system. System is given to you. Okay. You can carry out two types of different analyses. What are they? One is a steady state analysis. The other is a transient analysis. Remember, in the steady state analysis, okay, you require algebraic equations. Okay, you require algebraic equations. Yes or no? To analyze the system, okay, to analyze the system in steady state or using steady state analysis, definitely you require algebraic equations. And again, the system might be a linear system or nonlinear system. Yes or no? Okay. If it is a linear system, you require linear algebraic equations. If it is a nonlinear system, you require nonlinear algebraic equations. Understand? Okay. So, algebraic equations. In that algebraic equations, again you have what? Linear algebraic equations. Yes or no? And nonlinear algebraic equations. Nonlinear, okay? Nonlinear algebraic equations. Okay? Now, transient analysis, you require differential equations. Generally, the mathematical models, the mathematical equations required to analyze the given system using the transient analysis is you require differential equations. Again, the system might be a linear system, non-linear system. Okay? Linear system or non-linear system. Now, you require for a linear system linear differential equations. Now, non-linear system, non-linear, okay, non-linear differential equations. You understand? Linear differential equations, non-linear differential equations. Understand? Okay. Linear differential equations can be solved, okay, can be solved using Cramer's rule, okay, Gauss Jordan, Gauss elimination, Cholesky. There are so many methods of them. Okay. Now, nonlinear algebraic equations are solved by Gauss-Seidel, Newton-Raphson is the most powerful method. Okay, that is iterative techniques. Okay, iterative techniques, iterative methods. Okay, particularly NR method is very, very powerful. Newton-Raphson method is very, very powerful. Now, linear differential equations. Linear differential equations can be solved by complementary function plus particular integral method. Okay. Yes or no? You have complementary function, particular integral, and so on and so forth. Okay. And nonlinear differential equations can be solved using, okay, again iterative method. In that, the Newton-Raphson is the most powerful method. Newton-Raphson is called generally a parent algorithm. It's the most powerful algorithm. Still, people are using it, okay, because it is very, very, strong enough to reach the convergence within just 3 iterations. You give any complex network, any complex system, irrespective of the size of the system, within that, iterations only it will solve. And particularly for nonlinear differential equations, it can be nonlinear differential equations can be solved using iterative method, that to Newton-Raphson method. Newton-Raphson method is a very, very powerful method. You understand now? Okay. Steady state analysis, transient analysis. This is all about your engineering. Understand all of you? Okay. Now we are applying to a network. That is why I put a title network analysis. Otherwise, analysis of any given system. It doesn't matter whether it is a electric system or mechanical system or chemical system or biological system. Any system it might be. Okay. The analysis can be divided into 2 parts. So for steady state analysis, you always require algebraic equations. For transient analysis, you always require what? Differential equations. Okay. And the algebraic equations in this, linear algebraic equations for linear system, nonlinear algebraic equations for nonlinear system. Generally, in most of the cases, okay, we deal with only linear systems, but not the nonlinear systems. Even if you have a nonlinear system, you linearize with respect to or around an operating point, you linearize those equations, okay, using some techniques. How to linearize the nonlinear equations, again, there is a big topic again, okay. Similarly, linear differential equations for a linear system and a nonlinear differential equations for nonlinear system. Cramer's rule is the most powerful method in our class. We frequently apply. Okay, for 2 equations, 3 equations, the best method. For again more than 2, 3 equations, again I think the Cramer's rule is very difficult to apply. Okay, but generally in the gate you don't get more than the matrix size 3 by 3. Okay. Similarly, all these nonlinear algebraic equations. Okay, all these things. You're not going to get the questions on nonlinear networks. Okay, we have only linear networks. Okay, so this is all about it. And steady state analysis also, we have DC and AC steady state analysis. Here also you have DC and AC transient analysis. You have DC circuits and sinusoidal, DC excitation or sinusoidal excitation. Here also DC excitation, sinusoidal excitation. That's it. So please, all of you note down this. This is all about engineering. Okay, you please note down this. One should have a command over the entire picture. Okay, you must have everything in your mind that how the analysis can be carried out. I'll give you time. Please note down this. Now, where are we? Actually here, DC circuits and that too steady state analysis. So, DC steady state analysis, now we are in, and that we will discuss now. Okay, now let us start. Let us start. We are now in steady state analysis, that too DC. In that linear. So, what do you want now? Tell me. Now, what do you want actually here? Network analysis, DC, linear. We require what? Linear algebraic equations. Okay, how we solve them? Cramer's rule. Now, again, these linear algebraic equations can be obtained using mesh or node. There are 2 different ways to obtain the linear algebraic equations for a given circuit. Using mesh analysis, you can obtain. Using node analysis, you can obtain. And each method is having an advantage and disadvantage, no doubt in that. That we will see. And later we realize for a given network, which method is going to be the best method, that we will decide. I think you are going to decide after my explanation. Okay, for a given problem, which method is the best. Now the first method, okay, what is this? Mesh analysis. Put the heading, mesh analysis. The first method, mesh analysis. Mesh analysis. Write on the point here. Write on the point here. Whenever you see mesh analysis, these 2 points must be printed in your mind. The first point is the linear algebraic equations. The linear algebraic equations. Because ultimately what do you want in the analysis? You want the equations, that's it. Okay? Because you are dealing with steady state analysis, therefore algebraic equations. And you are dealing with a linear system, therefore linear algebraic equations. Okay? So the linear algebraic equations are obtained using KVL, Kirchhoff's voltage law, plus Ohm's law. Ohm's law is default available, okay? Without Ohm's law, you can't do anything. You cannot obtain any equation at all. That is obviously present. But what is main here? KVL. Suppose in the 4 options, okay, you are given KVL, KCL, Ohm's law, okay, D, KVL plus Ohm's law. What is your answer? Obviously, this is going to be your answer, right? Suppose if the options are given like this, okay, KVL, B KCL, Ohm's law, D, none. What do you choose? You can choose KVL, there is no problem. Okay? So don't worry about that, because he is not mentioning that KVL plus Ohm's law, but instead he is mentioning KVL in the 4 options. You can go for KVL. By default, Ohm's law is there. There is no need to specifically mention Ohm's law. Understand? Okay? It means that his intention is that KVL is there and Ohm's law is by default available. Okay? But if in the 4 options, if 2 options are given like KVL and KVL plus Ohm's law, you can give priority, or you can prefer this particular option instead of this option. If this is not available, but you can select this KVL directly. Okay? Do not worry, do not get confused. Okay? So therefore, in this mesh analysis, the linear algebraic equations are obtained using KVL plus Ohm's law. Now, another important point. Mesh analysis is applicable to planar networks only. Planar networks. Okay? Only. But not to non-planar networks. Non-planar networks. Okay? But not non-planar networks. Okay? So this is the disadvantage. What is the disadvantage of mesh analysis? If somebody is asking question, you must tell that it is applicable to only planar networks, but not to the non-planar. But you must also understand what is planar and what is non-planar. Okay? So write down planar network. Put the heading planar network. Write down planar network. Write down. It is the one that can be drawn on a plane. I repeat, it is the one that can be drawn on a plane with no branches crossing over the other. It is the one that can be drawn on a plane with no branches crossing over the other. Okay, that's planar network. Next one is what? Non-planar network. Put the heading non-planar network. Next one is non-planar network. It is the one that can be drawn on a plane. It is the one that can be drawn on a plane with one or more branches crossing over the other. With one or more branches crossing over the other. Okay, I think it's very clear. It is the one that can be drawn on a plane with one or more branches crossing over the other. That is a non-planar. But whereas in the first one, no branches crossing over the other. Okay, we will see now the examples. Okay, some examples we will see. Which of the following are planar or non-planar? Now look at this. Is it a planar network or non-planar network? Let us decide. Okay, is it planar or non-planar? Okay, how do you identify whether it's a planar or non-planar for a given network? How do you identify? Definitely when such kind of questions are given, he will intentionally give you the crossing over the other, one branch crossing over the other. But only thing you have to check, whether that crossover can be eliminated by reconstructing the network or not, without violating the rules. And of course, no reduction, nothing again. You can't use star data transformation, you can't use any other technique, you can't use any reduction method. Okay? But just by reconstructing the network, can we really eliminate that crossover or not? That we have to check. Look at this. Now, this element and this element, you see, this is crossing over this element. But can I draw this element something like this? Yes, there is a possibility. When I draw again this network, reconstruct the network, After reconstructing the network, if this network doesn't have any crossover, okay, then I can say it is a planar network. Okay. But if I find any crossover even after reconstructing the network, all possible ways, all different possible ways I tried, okay, all different possible ways I tried, but still I did not, okay, I did not eliminate that crossover, then I would say definitely it's a non-planar. Okay. So second example, you see, you will understand the second example, third example. I just give here. Look at this. Okay. Let me say this is R1, this is R2, and all remaining elements are there. I don't want to name them. Okay. Just these two are very important here. So what happens here? You find crossovers. I told you immediately just looking at the network and because you found some crossovers, don't call it non-planar. You make an attempt first. Whether it is possible to redraw the network eliminating that crossover or not, that you have to check. Okay, look at this. Is there any possibility? Suppose, can I take this R1 and draw at the same point because this point is connected here. If I remove it, then I have to connect it again. I have to connect like this. Again, I am crossing this. Crossing this. Yes or no? Something like that. You see any different possible way this R1 can be connected again with a crossover. But you see here, this particular one, you see this particular one, this R2 can be removed, and since this point and this point both are operating at same potential, yes or no? Yes or no? Therefore, can I eliminate this and draw across this? Suppose if it is R3, can I connect across R3 here? Look at this. So this is very, very important observation. Okay, my dear students, this is very, very important observation. Look at this. This is what actually there, R1. Now this is R3, right? Okay. R3. Now R2 I would like to construct across R3 only. Do you have any objection? This is R2. Hope you understand the point now. Because this point and this point both are operating at same potentials. I can remove it and connect across it. That's it. Then the crossover is eliminated. After reconstructing the network, the crossover is not present. So therefore, it is still planar network only. Understand all of you? Okay. Now suppose I construct like this. Third example. Look at this, all of you. I give you time to note down. Don't write. The first instance itself, you can identify whether it is a planar or non-planar. Now I am inserting a resistor here. Now look at this. In the previous example, this point and this point was operating at same potentials because there was a zero resistance path here. But now I inserted one resistor here. Now you cannot really move this resistor to this point because now there is a resistor, there is a potential difference. They are not operating at same potentials. So neither you change this R1, nor you change R2, nor any other combination you take here, any other reconstruction you take now, any modification you make, still you cannot escape from the crossover. Okay? Therefore, it is definitely a non-planar network. Such networks cannot be solved by mesh analysis. Understand? Such networks cannot be solved by mesh analysis. Okay? So please note down these examples 1, 2, 3 for planar and non-planar quickly. So what is the disadvantage of mesh analysis? It is not applicable to the non-planar networks. It's not possible to apply. Okay. Only to planar networks you can apply. We will see different cases. I know that most of you are aware of how to apply mesh analysis to a given network, but still I discuss from the basics as if you are a beginner. Okay. I know that you are not beginner, but still I discuss keeping in mind all category of students. Okay. All categories of students. Now, look at this, all of you. Let us look at step by step procedure. Step 1, step 2, step 3 procedure. Okay. Now, how to apply mesh analysis to a given network. Let me discuss each and every point here so that there is no confusion at all. Okay. Look at this. Step 1. We would like to get the linear algebraic equations. Those linear algebraic equations must be as minimum as possible so that you can save the time. Minimum number of equations we require. Yes or no? Okay. So therefore, choose minimum number of loops. Using a formula L is equal to B minus N plus 1. What is B stands for? Number of branches. What is N stands for? Number of nodes. What is L stands for here? Is it simply number of loops? No, number of fundamental loops. Or basic loops. In network topology, okay, in network topology terminology, you generally call it what? Links, number of links. Okay. So choose the minimum number of loops. How many loops are there? You can see number of branches 5, nodes 1, 2, 3, 4. So 5 minus 4 plus 1. Okay. What is this? Actually 5 minus 4 plus 1. Then you get two loops. But you don't need to count like that. You can see how many 1 and 2, how many closed paths are looking. Okay. That's it. 2 you can choose directly. Okay. Now, we need to even choose the loops. How many loops are there? 1, 2, 3. There are 3 loops. But how many fundamental loops are there? Only 2. You can choose minimum number of loops. That means as many loops as the fundamental. But those loops not necessarily be only fundamental loops. You understand? Okay. See. 1, 2, 3 loops are there. This is also a closed path. This can also be called as a loop. But while choosing the loops, you have to select only 2 in this example. Whether you want to take 1, 2 or 1, 3 or 2, 3, that is of your choice. That is why you also write down that choose the loops and their loop currents. In either clockwise or counterclockwise direction. So for this particular one, I am choosing 1, 2. I am calling this 1, 2. This is 3, okay, but I am choosing 1 and both of them I am choosing what? Clockwise direction. Now, step 2. Step 2. Mesh analysis deals with what? KVL. KVL deals with what? Branch voltages. Okay. Now branch voltages. Algebraic sum of branch voltage in a closed loop is 0. But to find branch voltage, you require branch currents. Yes or no? Now the branch currents are expressed in terms of loop currents. Hope you understand the point, the sequence here. Mesh analysis deals with KVL. To apply KVL, you require branch voltage. Algebraic sum of the branch voltage in the closed loop is 0. Okay. And to find a branch voltage, you require a branch current. Now the branch currents are expressed in terms of loop current. You understand? Okay. Now look at this. Now look at the second step. What we are supposed to do now? You are supposed to express now branch currents in terms of loop current. Then you find branch voltage. Then you apply KVL in the selected loop. Okay. So therefore, step 2, write down here, express branch currents in terms of loop currents. Okay. And also find branch voltages. Please write down this, all of you, along with me. Okay. Express branch currents in terms of loop currents and also find branch voltage. Once you find branch currents, you can find branch voltages. Yes or no? Okay. Now once you find branch voltages, you can go for what? Apply KVL. In which loop you apply? Apply KVL. In which loop? In fact, you can apply KVL in any loop that you want. Because what is the statement we have given? If there are 100 loops, you are supposed to, okay, the 100 loops, if there are 100 loops, then in 100 loops the KVL must be satisfied. Yes or no? I've got 99 loops satisfied, but one loop is not satisfying. It is an invalid circuit. You know already that if KVL is not satisfied, what will happen? Okay. Therefore, apply KVL, okay, any loop, but we always recommend to make it more systematic. To make it more systematic, okay, we can always apply, or we can always recommend to apply in the loops that you have chosen, selected, right? Which loops you have selected 1, 2, right? Better you apply KVL in those loops only. But it is not compulsory that you apply only in those 2 loops. You can apply in any loops. Okay. So apply KVL in the chosen loops. And solve for I1 and I2. Once you get loop currents, you can play with the network. Anything that you want, you can really get. Okay. So now let us try to execute it. I think all of you have noted down this, right? We can execute it now. How do we execute it? Okay. Let us first express the branch currents in terms of the loop currents. You see, I1 is flowing in this loop. What does it mean? I1 is passing through R1, R3, E1. I2 is passing through R2, E2, R3. Now there is a standard representation here. See, some current I1 is flowing. What does it mean? These elements belong to first loop. These elements belong to what? Second loop. The elements belong to first loop. What are they? 1, 2, 3. That is R1, R3, E1. The elements belong to second loop is what? R2, E2, R3. Yes or no? Okay. But the elements belong to both first loop and second loop is what? R3. Yes or no? All of you, okay. The elements belong to only first loop is what? R1 and E1. The elements belong to only second loop is what? R2 and E2. Okay. Now you can see here the elements belong to only first loop will have the branch current same as the loop current. That means this is going to be I1 in the same direction. The elements belong to only second loop will have the current that is same as its loop current. The elements belong to both first loop and second loop, okay, will have the resultant of the loop currents. So I1 is flowing downward, I2 is flowing upward. They can say I1 is greater than I2 if you assume then I1 minus I2 is the current flowing in the downward direction. You understand? Once you know the branch current, you know the branch voltage with the polarities. Okay, how do you decide the polarities here? Based on the direction of the current in the passive element. Yes or no, all of you? Okay, so this is how you can represent the second step is executed express the branch currents in terms of the loop currents and also find the branch voltage. Okay. So I stop the session here because the time is over here, and in the next session I'll continue the same thing. Okay.